All right. So, your homework is due soon. I realize this problem set is very challenging and has some intense amount of work to get it done. You know, my point here is to give you exposure and opportunity to explore and learn. This is not about testing you, evaluating you, you know, I'm an easy grader. It's really about you just doing my best to give you the exposure to things that, so you can learn what you want to learn and give you the opportunity to do it. So don't stress out about it too much, okay? It's really, this is for you guys to, you know, get the opportunity to learn some things and do with it what you will, okay? All right. The next assignment will be a shorter one for just a week before spring break, and then we'll take a break, all right? All right. Very good. So, we are talking about now a very important problem, both from a foundational point of view and from applications point of view, of thinking about quantum mechanics with multiple degrees of freedom. Okay, so we're starting to talk about the problem of entanglement. And so in particular, we think about 2 degrees of freedom. We call that a bipartite system. It has 2 parts. The 2 degrees of freedom are 2 parts. Okay? And so just to set the stage, we talked about just the simplest possible example that you might get in elementary quantum mechanics, where you think about 2 particles moving in 1D. Okay? And the way we can have some wave function for those 2 particles in position representation, and think about the joint probability density for finding those 2 particles. I've called these positions now A and B rather than 1 and 2 because it was getting confusing, I think, last time in the presentation. Okay? And one of the things that we saw of interest, just from standard statistics, I can talk about what are called the marginal probability densities. Okay? So these are, if I have a joint probability distribution for 2 random variables, I can ask about the marginal probabilities for one or the other of the random variables, irrespective of what the other one is. And we get that by marginalizing the distribution, right? By summing over all the values associated with the other, and that's the so-called marginal distribution. Okay? So for the particular case, if we had what our wave function was a product state, where we had a wave function for particle A and a wave function for particle B, then the joint distribution is just the product of the probability distribution, and those are the marginals as well. Right, because if I marginalize, if I sum over B, this is 1. When I sum over A, that's 1, and those are marginals as well. Okay? On the other hand, if we have a state that cannot be written, a pure state that cannot be written as the product of 2 wave functions, then we say it is entangled. Okay? The pure states that are product states are separable. Now I keep prefacing this by pure states that are, because there's a real subtlety there, which we'll come back to, which many of you are familiar with, but not everyone is. Okay, so here is an example of such a state. This state is a superposition. We can think about this as two particles in a harmonic oscillator that are distinguishable and not identical particles. We don't have to worry about Bose or Fermi statistics or anything like that. Where one of them is in the ground state and the other is in the excited state, but I don't, the first excited state of the harmonic oscillator, but I don't know which it is, okay? And there's some probability amplitude associated with each of those cases, all right? Then as we showed, sort of, last time, if I asked what are the marginal probability distributions for finding particle A somewhere, or particle B but somewhere, these are the distributions. And what's important here for the entangled state, as we'll see in generalization in a moment, is that there's no wave function that I can assign to A and a wave function to B such that I get the marginals right, such that the square of that is the marginal distribution, at the same time that the marginals put together is the joint probability distribution. I cannot construct the joint distribution from its pieces. And that is an important hallmark of entanglement, which we will try to probe more deeply. What does that mean exactly? Okay? All right. So to get at this formalism, we're looking now in thinking about this from the point of view of now Dirac notation and general notation of Hilbert space. We're looking at bipartite systems. These two parts, or two degrees of freedom, they're sometimes called in the jargon subsystems. So each degree of freedom is a not a subspace, excuse me, but a subsystem. And this is the joint system. Okay, so that's a jargon that we use. Okay. So these are two subsystems that are going to be the joint system, excuse me, of the two together gives me the total Hilbert space. So each of this is the Hilbert space for subsystem A, which could be infinite dimensional space or finite dimensional space, depending on what we're talking about. It could be, in the case here, these were infinite dimensional Hilbert space associated with motion, or it could be something like the spin of a particle, which would be some finite dimensional Hilbert space. We could restrict ourselves to a finite dimensional subspace within an infinite dimensional Hilbert space. Take two levels of a transmon and call that a qubit, for example, a two-level system. And similarly, there's a Hilbert space for B, and this is the joint Hilbert space for the two, the tensor product space. And we talked last time, I won't review it all, just to remind ourselves of how we deal with the tensor product of vectors and the tensor products of operators and all of that stuff, okay? All right, so importantly, this guy has some dimension of this Hilbert space, this guy has some dimension of this Hilbert space, and the dimension of the total Hilbert space is the product of the two dimensions. In this case, we didn't see that because both of them were infinite dimensional, so everything was infinite in the wave function case. We didn't see the growth in the dimension of Hilbert space when we looked at this wave function problem, because everything was infinite dimensional to begin with. Okay? All right, excellent. All right, so importantly, maybe I'll do this here. If we have this, is a basis basis for the Hilbert space HA, and this set of vectors is a basis for the Hilbert space little h sub b, then we can define vectors labeled by the indices I and j, where I just take the tensor product of this. This is a basis of the joint Hilbert space. And we'll call that the standard basis. Okay? Okay, very good. So, let's say that we have a state, a pure state, in the joint Hilbert space. Okay. This state can always be expanded in the spaces. Okay. So I can always write this vector as a superposition of the standard basis, this being the product basis. Okay. So this is a product basis. It's a product basis. Where, of course, these guys are just the probability amplitudes associated with that basis, right? Very good. So now, so I can ask, for example, the probability, the joint probability of, if I were to measure in that basis, I can ask what's the probability that I'll see this outcome. Outcome I on subsystem A and outcome J on subsystem B. Well, that's, of course, equal to the square of the amplitude. Right? Which I can always write as the diagonal element of the density operator associated with the state, right? That's the rule of how you find probabilities. We take the diagonal element. That's, of course, in this case, this is a pure state, and this is just equal to the density matrix, in this case, where the density operator is that projector, right? And you see that quickly just by looking at this times its complex conjugate, and that's force. Okay? So this is the joint probability distribution. For that particular set of outcomes. And we can look at the marginals, just like before, but instead of, in this case, it was a probability density, and we did an integral over this. Now, to marginalize, if I wanted to know what's the probability of seeing outcome I on subsystem A, irrespective of what the value of B is, how would I obtain that? Well, I would marginalize the probability distribution, right? And how do you marginalize the probability distribution? You sum over those values. So I sum over all the j's in this case. That's statistics. Right? That's how you marginalize a distribution. So in this particular case, this is equal to the sum over j times of this object, okay? Which I'll write out pretty explicitly at the moment. Let me not be confusing about whether I put things on the top or the bottom. Right? Everyone clear? So, now of course, in quantum mechanics, we have a rule. It's called the Born rule, which says if I want to find the probability of finding a certain outcome for measuring a system, I have the quantum state associated with that system, in this case the subsystem A, and to get the probability, this is the Born rule, right? That is to say, outcome I is associated with a certain basis, in this case, of values. Those are the measurements I'm doing. And to get the probability, there should be some quantum state assigned to subsystem A. And I get the probability by looking at the diagonal matrix element of that state. That's the rule if I'm measuring in a basis. There's a more general rule if I'm doing a POVM, but you know, put that aside for the moment. So what is rho A? Well, here it is. So I can move this inside and then say rho A is equal to the sum over J take this in a product. So this object is known as the partial trace. Why is it a partial trace and not the whole trace shebang? Well, it's because I'm only, so this is a little bit of a bastardized notation. This thing looks like a matrix element, and typically a matrix element is a number. But this ain't a number. This is an operator, right? Because I'm only looking at part of, I don't have the whole, I don't have the, I took this part of the tensor product out, okay? This is a formal object. It's known as the partial trace. And so what we say is that the marginal state, or the marginal density operator, we obtain by tracing out B. Okay, if I wanted to, if I asked now what is the normalization of this, I trace over A, then if I trace over A and B, that would be 1. But that's the total trace over both subsystems. This is the partial trace. So the partial trace, I did all this so that you see that this is nothing more than just the generalization of statistics of how you marginalize it. It's nothing crazy. It's exactly what you would do in statistics. It's just that we have this extra density operator-y thing that is a little bit more general. Okay? So I like to call this the marginal density operator. It's often called in the literature the reduced density operator. But I think the term marginal is more descriptive. Okay? And similarly, we could do the same thing and ask what is the marginal state associated to B. What is the state of the system that we would associate to B? And the way we would do that is we trace out A. And formally speaking, we would do these matrix, partial matrix elements. And of course there are matrix, I can write this, we've done this in terms of bras and cats, we can think about it in terms of the matrices themselves, right? I square those and then I have to do the sum over different indices. I can never remember how to do it, so I never write it in matrix way. We rarely ever do that anyway. We just let Mathematica do it for us, or something like that. All right, very good. Okay, cool. So, let me see what I want to say here. Okay, so suppose that I have a product state. So let's say that the joint state of the system is this. I can write, in that case, the joint density operator in the following way, as the tensor product of those two operators. Okay. So this is the pure state for A, and this is the pure state of B. So this particular pure state is a product state, or written in operator form. Here we wrote it as a tensor product of vectors in Hilbert space, and here I'm writing it as a tensor product of operators, density operators. Each of these are pure. The joint is pure, and each of the states associated with the subsystem. And if I marginalize this, I get exactly what I expect. So if I take the partial trace over, say, B, how do you do that partial trace? Well, here's how I do it. The old rule, but now only on B. Okay? So, is equal to see what I did? That's how you take the trace. And this is 1. Which, of course, is what we expect. And vice versa. I mean, you could see this many ways. Another way to do it, if I just take the partial trace with respect to B, I'm tracing over that, and if this is normalized, the trace over that is 1, and I get the same thing. But this kind of rule is useful, as we will see. All right? And similarly, in this case, if I look at the marginal by tracing out A, I get the pure state as expected. All right. All right, so this was an example, this was a product state, and such a state is, as we say, separable. A pure state that is not separable, which in this case means the same thing as product. They are one and the same for pure states, is entangled. Okay, so let's look at an example. Let's say I have two spin 1/2 particles, or qubits. Okay. So my joint Hilbert space is the Hilbert space associated with two spin 1/2s. All right. So, what's the dimension of this Hilbert space, this joint Hilbert space, by the way?
4.
4. Thank you, Zach. Excellent. All right. So, here's an example. Let's say I look at the spin singlet. That's one of the most famous entangled states there is, as we will see. We'll remind ourselves, we talked a little bit about EPR. We will talk more. So, this state can be written as a superposition of both spins up along Z, one spin up along Z, the other spin down along Z, minus the other way around. Okay. It's called the spin singlet because, as you may remember, this state has total spin 0 and projection along the Z-axis is also 0. There's only one state. This state has a total spin 0. So this is also an eigenstate of the total spin angular momentum with spin 0. Okay. All right. So what are the marginal states in this case? So let's, again, I'll call this AB. There's A, there's B, spin A, spin B. These spins have to be distinguishable and different traps or something so that I don't have to worry about anything about this minus sign has nothing to do at this point with Fermi statistics. Though if we had two electrons on top of one another in the same spatial orbital, then they better be in the spin singlet to make the thing antisymmetric under exchange. But put that aside. When we talk about subsystems, we're always thinking in this context of other degrees of freedom that make them in some way, if they're the same particle, that they're either two different kinds of particles or they're distinguishable in some way. So we don't have to worry about Bose and Fermi statistics. Yes?
What do we have to do if they aren't distinguishable?
Oh boy, I don't want to go there yet. It's complicated, what you mean by entanglement in that case. It's complicated. Put that aside for now. All right, so what is the state that we associate to, so that the joint state of the system, of the singlet, is this beast. Did I get that right? I think I did. Okay, so those are the four terms you get when you take the outer product of this with itself. Okay, and so now I ask you by I, what is the marginal state of spin A? How do you do it? The old thank you method. So 1, 1, 0, right? Because this is orthogonal to that. 0. So these terms go away. And I end up with this, which is, of course, the maximally mixed state. And similarly, the marginal state of B is the same thing, but on B, right? So, again, what we see here is this most incredible thing, that what we have here is a pure state and here we have mixed. What the heck does this mean? What this means is that as far as the state of the joint system is concerned, we have maximal information about the whole system. In other words, there's no missing information that we could get to better define the state. Of course, in quantum mechanics, that doesn't mean that every outcome is deterministic. Even when we have maximal information, if we don't measure, say, one of the eigenvalues of this, we're going to get a random outcome. Okay? Nonetheless, it's maximal. There's nothing we can do to better define what we're seeing. On the other hand, so the joint system here is maximal information, but the marginals are minimal information. These are the maximally mixed states. The most mixed, the most missing information I could possibly get. Means no matter what measurement I do on that spin, I'm going to just see a random bit. There is no outcome for which I can predict it's going to be better than a fair coin flip, no matter what I measure on that system. And that's a bizarre thing. What it's saying is we know everything about the whole, but nothing about the pieces. And that's something we couldn't have classically. Classically, if you know the whole thing, then you know everything about the pieces, how they're correlated together, everything about them. There is no way you can have this kind of knowing nothing about the pieces but knowing everything about the whole.
And where is the missing information?
Oh, well, we'll get to that in a moment.
Okay.
We're about to get to that. All right, so this is one of the hallmarks of entanglement, this idea that we can have a situation where we have absolute purity of the whole, but mixedness in the pieces. That's one of the hallmarks of entanglement. Okay? Another hallmark of entanglement, as you know, has to do, and this comes back, is the question of correlations. So, when we had something like a product state, so if I have, you know, the joint probability distribution is equal to, then we say that they are statistically independent. Right? That's the definition of, in statistics, of two random variables that are statistically independent if their joint probability distribution factorizes, right? So from the point of view of quantum mechanics, if I have a joint state of this sort, then, which is the separable case, then the measurement outcomes are statistically independent. Otherwise, we say that they're correlated, okay? And for a pure state, if you have correlations, you absolutely have entanglement, okay? Because we just said a pure state, which is not a product state, is an entangled state. And if it's an entangled state, then the probability distribution doesn't factorize, and therefore we have correlations. So for a pure state, correlations in the outcomes is in one-to-one correspondent with entanglement. But these correlations, as you know, are quite different from classical correlations. Okay? So let's just quickly review the idea of the von Neumann projection. If I measure in a basis which has projectors corresponding to the different outcomes, they could be the eigenvectors of a Hermitian observable, for example. Let me call this, not to confuse with my other, let's call this alpha, just a general thing, not necessarily that basis. And I say, I want to know what is the state if I conditioned on that measurement. What I do is I project onto that, whatever the state was before, and then I renormalize it. Right? For a so-called projective measurement. We'll talk about things beyond projective measurements in a little bit. And if I had thought about it from the point of view of the density operator, I would project on both the bra and the ket, and then renormalize. Okay. So, if if we think about our spin singlet here, with our two spin 1/2s, and they fly apart, and there's an observer here who is always affectionately known as Alice, and the other observer here who's affectionately known as Bob. And if you need a third person, it's always Charlie. I used to have a Bob and a Charlie and a Lee, and I wanted Lee to change her name to Alice, but she would never do it. Anyway, so Alice can make a measurement on her side with some kind of Stern-Gerlach device, for example. Right? So if Alice does such a measurement, so let's say that they know, they agreed, both observed this machine, and they know that it's prepared these spin singlets, and it sent the two spins. They each went off to their respective sides of the galaxy, or wherever, the lab, I don't know how far apart they want to be, and Alice does her measurement, okay? So let's say that she measures in the basis, spin up, spin down along Z. Of course, they have to have the common reference frame. They have to know what direction Z is and all of that. And they have to have a line that's a whole nother story. So she's going to measure along Z. Okay. So if she does that measurement and she sees spin up coming out of her Stern-Gerlach device, then what state would she say is the joint system? Well, what she would say is the joint system conditioned on having measured this on subsystem A would be, I would project my singlet state onto that and then renormalize. And when I do that with the spin singlet on this case, so here's the state, I'm just going to get this term, because term is going to be 0, right? And then I renormalize it, and I'm going to get spin up along Z, spin down for Bob. Okay? And similarly, if Alice does that measurement and finds spin down along Z, then doing the same thing up to some overall phase that I don't care about, but if she wants to, she can keep it. Okay. So, of course, what this says is that once Alice makes her measurement, she knows that if Bob were to make the measurement along Z, what he's going to get. If she finds A, she knows, if she finds up, she knows he'll find down along Z, and vice versa. Bob doesn't know. Bob sees a random bit. But if they call them up, each up over the intergalactic phone, at some point they can check, and they will see that indeed their measurement outcomes are correlated in this way. So you might say, all right, that's nice, but who cares? I mean, this state would do the same thing. Suppose I had the state rho, which was 50% of the time I have this state, and 50% of the time I have this state. From the point of view of what I just described, this state would show the same kind of correlation, right? if she measures spin up along Z, she knows for sure Bob finds spin down along Z. And if she measures along Z and finds spin down, then she knows. So what's the difference between these two? This is also correlated. There's a correlation between Alice's measurement outcome and Bob's measurement outcome. But I claim that this is classically correlated. Whereas this, the singlet state, was entangled. Yeah?
So I guess if you look at this this big density matrix,
Uh-huh.
this would be diagonal in the standard basis?
It is.
Whereas the other one has coherences.
It does. So what are the implications of that? I mean, so I just want to do a little experiment here, okay? So everyone sees I have this anticorrelated. There's a red cap, I mean a black cap and a blue cap, okay? Okay. Matt, come over here. Close your eyes, okay? All right, very good. Remember, there was a black cap and a blue cap, okay? Then close your eyes. Okay. Okay, open your eyes and instantly say what the other color is.
Blue.
Blue. But the other color is
Yeah.
not the one you have.
Yeah, all right. One more time. What is Ben's color?
Black.
Right,
Blue.
that's right. All right. Sorry. All right. Happens every time. So, you know, you knew what he was going to find instantly. Who cares? I mean, they were correlated. This idea that somehow you're forcing that to come has nothing to do, it's just the fact that they were correlated, okay? But there's something more. I mean, those coherences that Matt, so obviously, coming back to this board over here, the state that I just described was this one. It set these guys to 0. From the point of view of the specific experiment, the Gedanken experiment that I just described, there's no difference between them. So what is the difference? What experiment could Alice and Bob do for which they would see different results than with the singlet than with this state? Measure in a different basis, right? So if instead she oriented her Stern-Gallagher apparatus along X, right? Well, then something different would happen, because in fact, because it's a spin singlet and it's a spin 0, it means that it is rotationally symmetric. And I can write that correlation in any direction. So in fact, it is the case, just applying the rotation operator to the state, that the singlet can be equally well written as a superposition of spin up and spin down along any direction, whether this is X, Y, Z, or any direction on the sphere I like. By the way, often we're too lazy to write the O times in there and just put the two kets next to one another, and we know that that makes sense or product. Okay, so that spin singlet is this as well, which means that if Alice were to measure, in this case, along X, then this is the post-measurement state, right? Which which is equivalent to, you know, up, up, down, down, along X. But what would it be in this case? If this were the state, would it be that? How would you get what it is? Well, you have to use this von Neumann thingy, Mahoosit, wherever the hell that was, is probably the bad professor erased it. You have to have you put the product, you know, the projectors on each side. And that state's going to be some other mixed state. It's not going to be, this is a pure state. So, there's something different about quantum correlations versus classical correlations. And we also see here why just saying something is a product state or not is not enough in the context of mixed states to say whether something is entangled or not. This density matrix has correlations, but it's not entangled. But it's not a product state either. What is it? It's a convex combination of product states, right? This is equal to, you know, a half rho, I say up Z A, down Z B, and then 50%. This was my preparing the blue and black caps. That's a perfectly good preparation procedure, but this state is separable in the language of quantum mechanics because it's not entangled. But it's not a product state. You see, this is a statistical mixture of product states. Anything that is a statistical mixture of product states is a separable state, which is to say, not entangled. We really need, I hate the word separable because you think separable means it can be separated, it's uncorrelated, but it just means not entangled. Which is to say, it is a statistical mixture of product states, as opposed to a coherent superposition of product states. A coherent superposition of product states is an entangled state. But a statistical mixture of product states is just a classically correlated state. Now, the implications of entanglement, of course, are incredibly profound. This idea that things are correlated in this way that are beyond classical correlation is the most profound aspect of quantum mechanics. And it's, in some sense, part of the answer to Manuel's question, where is the missing information? So, the missing information that Alice and Bob don't have is in the entanglement. It's in the correlations. That is somehow a non-local thing. It's in the joint system. They don't have act locally. They have a random spin, a totally thermal spin, a spin with as if it were at infinite temperature. But the missing information that makes the joint system have zero entropy and effectively zero temperature is in how they are superposed. It's in the correlations. Okay? And that's something we can't have classically. We can't have marginals which are statistically mixed, but the joint being completely a definite outcome. Right? Which is what it would mean to be a pure state in classical statistics. So one of the takeaway messages here also is, you know, when we introduced the density operator last semester, one of the ways we did it was we just imagined a preparer, okay? We imagined there was a black box with preparer in it who could flip a coin. And that coin could be flipped and send to the observer a spin up or down, for example, along a direction. And for example, if it was a fair coin, then, and just a completely random 50-50 chance, then the state that we would assign to the spin that would determine the probability of measurement outcomes would be a completely mixed state. Where is the missing information there? The coin, right? I mean, the preparer, from the preparer's perspective, it was a pure state. She knew whether she sent up along Z or down along Z, for example. The observer didn't have that information, and so the observer assigns a mixed state. The preparer would assign a pure state to it. Okay? On the other hand, the exact same kind of statistics are what we would see from the point of view of the observer here in this singlet. Thus, no matter what measurement the observer did over here, she would see a random up or down. And it was as if the person inside the box flipped the coin and randomly sent up Z or down Z. It would be exactly the same measurement statistics that that this observer would see. And that's an amazing thing, right? It's saying that we see that the missing information can be from preparation, but we can effectively say missing information gets lost in entanglement. And that's going to be a very important concept when we think about the idea of the loss of quantum coherence. The process of decoherence is a process by which quantum coherence gets lost in the entanglement of the system with its environment, and thus becomes mixed as a precursor of things to come. Okay, let's continue. All right. So, now, whether or not a state is entangled or not, say a pure state, if it's a mixed state, it's really hard to tell whether or not something is classically correlated for quantity. For a pure state, it's doable, but it's not immediately obvious. For example, let's say that I have the state for my 2 qubits, which is the following state. And again, this just means tensor product, okay? This is a shorthand for I'm not writing the Z. It's good. Now you might look at this and say, well, yeah, this state looks entangled, right? It's a superposition of lots of product states. But in fact, it's not an entangled state at all. So let me just be more explicit here, put the z's on here. This state is equal to the state up y, tensor up y. Right? Because up y is 1 over root 2 up z plus I down z. So if I take the tensor product, well, no, I got it wrong. Gotta have the minus sign. Now it's that. Okay? So, you see, it's not obvious. And what if it was a plus sign? Would it be entangled? Yeah, probably it is. But it's not obvious in this way. So how do we know whether or not the state is entangled, and by how much it is entangled? Well, to do that, there is, for the case of bipartite pure states, there's the whole story is the Schmidt decomposition. That's everything. Everything you want to know about entanglement when you're talking about bipartite systems for pure states is the Schmidt decomposition. So let's discuss that. So, let's say that I have a pure state of my bipartite system. And as we said, that can be expanded in a product basis. Okay. Let's say that it's finite dimensional. Okay, so I and j go up to the appropriate dimensions. So this set of coefficients, which are in this case, you know, those coefficients for this four-dimensional case, are the elements of a dA by dB rectangular matrix. It could be square if dA equals dB, but in general, it's a rectangular matrix. Okay? So our goal is to see how much entanglement this is. It's not obvious, as we just described. But the whole thing I can do is to use what's called the singular value decomposition. So the singular value decomposition is the generalization of diagonalization where you don't have a square normal matrix. You can always do this, okay? And so the singular value decomposition, let's say, I'm going to say this matrix, I'll use bold-y double to say this is a matrix. I mean, do better than that, really. Okay, so that's a matrix whose elements are this. Okay, so this matrix can be decomposed in the following way. A unitary matrix, I'll take the transpose of it, this matrix, and another unitary matrix. So these are unitary. Oops, no, I don't want that. I want a diagonal. this is really diagonal in the following sense. So this thing is a dB by dB matrix. This guy is a dA by dA square matrix. They have to be that to be unitaries, they have to be square matrix. And this is the diagonal matrix that is rectangular that's dA by dB, okay, with the non-zero diagonal elements, which are called the singular values. Lambda mu, where lambda mu goes from 1 up to some, or mu up to some maximum value, where the maximum value is bounded from above by the minimum dimension. So the most non-zero singular values I can have is the smaller of the two dimensions. So if I had a cube bit and a cube trit, a two-dimensional and a three-dimensional system, the most non-zero singular values I can have is what? 2. Okay? This is a theorem of linear algebra. The way I find these things is the following.
Is this something we can always do?
Yes.
Any matrix?
For any complex matrix. Always. It's not like diagonalization, which is true for Hermitian or unitary matrices, or more generally what are called normal matrices. The singular value decomposition you can always do. And here's how you do it. First you try to find the board that you can erase. Guess I will not use that. Okay. So, let me just, here's an easier solution. Okay, let's look at taking this matrix and multiplying it by its Hermitian conjugate. Okay, with that decomposition. When I take the conjugate of that, they'll have a U dagger U. The transpose doesn't matter. It's still a unitary matrix. And that'll be 1. And what I'll get is D dagger, D dagger, D, V. Right? This matrix here is Hermitian. Right? And this is a dA by dA matrix, square matrix. And it's diagonal because this guy was diagonal. Okay? So what is V? V is the similarity transformation that takes me. So what I do to find the singular values is I take the rectangular matrix, I multiply, if it's a complex matrix, I don't just multiply it by its transpose, I multiply it by its complex transpose. And then diagonalize it. Okay? So, once I diagonalize it, V tells me how to get from one to the other. And similarly, I can diagonalize it the other way around. at it this way. U star is also a unitary matrix. I diagonalize this. This is going to have the same eigenvalues. This is a dB by dB matrix with the same non-zero eigenvalues. And those eigenvalues, if I take their square root, I get the singular values. And the U and V tell me how to go from the, or in this case, V, yeah, so the U and V tell me how to go from E, A, and Fj to the eigenvectors of D, D dagger, and D dagger D. So the way that I do the singular value decomposition, if I wanted to, is I take the matrix, multiply it by its conjugate, and diagonalize it. The eigenvectors are important, and the eigenvalues, their square roots, their positive square roots, these are all positive numbers, are the singular values. Now let us see why. Let's go to this board. Let's leave that there. How this gives us the entanglement. And we're going to pick this up again next week. So let's look at psi AD is equal to the sum over I, sum over J, gamma ij, EI, tensor Fj. But the matrix elements of this are the following. U transpose I mu, lambda mu, delta mu nu, d nu j. So this is my diagonal. This is my diagonal matrix. It's diagonal. It only has non-zero elements on the diagonal. And these are the matrix elements of this. Sum over mu, sum over mu. Okay? Times EI Fj. So, what does this equal? Well, now I can only have to sum over one index, and I get lambda mu, sum over I, u mu I, that's the transpose, that's why I took the transpose in the first place, tensor sum over j, v mu j, because I've set mu equals to nu, fj b. And we will call this thing u sub mu a, and this V sub mu V. And so the final answer is that the joint state is equal to a sum over this of the singular values U, A, tensor, B. Let's quickly analyze that for 3 minutes or less and understand what this is. How is this expression different from this expression? This guy has a sum over 2 indices. This guy has a sum over 1. That's kind of really important. Importantly, these things are called the Schmidt vectors. Notice, very important. The Schmidt vectors depend on the state. Here, this was an arbitrary basis. I didn't care what the state was. Some basis. I could take that state and I can decompose it into this basis. But these vectors depend on the state because the particular unitary transformation I did came from the singular value decomposition, which was dependent on these coefficients, which define the state. So this is a state-dependent decomposition. There will be generally different Schmidt vectors for different states. But if I know the state, I could do the singular value decomposition, and then if I wanted, and then I would find these vectors. Notice that the phase of these is defined. The phase is important because it's in here. These unitary transformations tell me what the phase is because these things are real and positive. So the actual phase in the superposition is buried in here. It's buried through this unitary transformation. And this, my friends, is the whole story of bipartite entanglement. And we'll explore that in more detail next week. But with the Schmidt decomposition, I know everything there is to know about the amount of entanglement there is in the system. How many people have seen this before? It's important. It really, if we want to understand things about entanglement, we got to understand that. All right, gang. Have a good afternoon.